Let S1 and S2 be finite subsets of some vector space. And S1 is a subset of S2. Then the following two statements are true. If S1 is linearly dependent, then so is S2, and if S2 is linearly independent, then so is S1. Now, I distinctly remember doing this proof when I was an undergraduate student 75 years ago, or some number of years like that. Let's see if I remember the proof. Okay, so first, let us get our diagram. We have our vector space. We weren't given a name. And we have S1, S sub 1 lies in S sub 2. Okay. So now, if S1 is linearly dependent, well then, yeah, so will S2. Because I can find the set of vectors in S2. I can find the linear combination of vectors in S2 where the coefficients are not all 0 that equals 0. Okay, proof of the first one. Suppose S1 is linearly dependent. Suppose S1 is equal to V1, V2 up to V sub k. Since S1 is linearly dependent, there exists C1, C2 up to C sub k, not all zeros, such that C1 V1 plus C2 V2 all the way up to CK VK is 0. That's the definition of linearly. That's the definition for this set to be linearly dependent. I can come up with a linear combination of V1 through VK that adds up to 0, and not all the coefficients are 0. So this is very important. Okay. Now, S2 is equal to V1, V2, up to V sub k plus other vectors. We'll stay in the same numerical order. V1, VK plus 1, VK plus 2, all the way up to V sub n. These vectors are in S1 and S2, and these vectors are only in S2. So these vectors that I underline in blue, they live out here. They're in S2, but not S1. And these vectors, which I highlighted in yellow, those are the vectors that live just in S1. But you know what? They're also in S2. So in S sub 2, C1 V1, this equation is valid. C1 V1 plus C2 V2 all the way up to CK VK equals 0. You know what? If you want me to use all the vectors in S2, I don't have to, but I can. I'll say 0 times the blue vectors, 0 times VK plus 1, plus 0 times V sub k plus 2, all the way down to 0 times Vn, and this is 0. But not all the C sub i's are 0. So S2 is linearly dependent. Now, for the proof of 2, let's see what's going on. This time you're told S2 is linearly independent. That is, the blue and the yellows are linearly independent. So how could you possibly come up with the linear combination of vectors in S1, or how can you find a set of vectors in S1 that are linearly dependent? That contradicts the fact that S2 is linearly independent. Okay. So, since S2 is linearly independent, if C1V1 plus C2V2 all the way up to CKVK all the way up to CNVN equals 0, then C1 equals C2 all the way up to equals Cn equals 0. The coefficients must be 0. That's because linearly independent says so. Okay, so I want to show that this set is linearly independent, linearly dependent. Okay, well, suppose, maybe I didn't even need this statement. Okay, suppose that C1V1 plus C2V2 all the way up to CKVK equals 0. So we're going to do some contradiction here, where not all CI's equal 0. But then C1V1 plus C2V2 all the way up to CKVK plus, let's change the color, plus CK plus 1, oops, I want all of these to be 0, plus 0 times VK plus 1 plus 0 times V sub K plus 2 all the way down to 0 times Vn equals 0, and not all CI's equal 0. But this is nonsense. Since V1 up to Vn is a linearly independent set. That is, since S2 is it, since S2, which equals this, is a linearly independent set. Hence, C1, C2 up to CK must also be 0. Hence, C1 equals C2 up to CK equals 0, which implies that V1, V2 up to VK are linearly independent, which implies S1, which is this set, is a linearly independent set. So it seems like I remember a little bit from my college days. I take it my linear algebra teacher did a good job. If you want to see theorems like this proven all day long, you can watch them. It's a no-brainer. Subscribe to my channel. See you folks in the next video. Watch and learn.